Welcome to today's webinar on Foundation Design in SAFE. SAFE is a powerful structural engineering software widely used for the analysis and design of concrete foundations and floor systems. In this session, we will explore its key features, modeling techniques, analysis process, and design workflow through some examples. Whether you are a student or a practicing engineer, this webinar aims to provide valuable insights into efficient foundation design using the SAFE. Thank you for joining us, and let's get started. The objectives are very simple. The more focus will be on the design, as well as some modeling and analysis aspects that are required for the design. Implementation of IS 456 will be covered in this discussion. So program usage and path to the design is very typical to the ETABS program, which we are conversant with. So the modeling that involves definitions of material properties, section properties, load pattern definitions, spring definitions, and creation of the model, the geometry, and assignments of loads and other property-related assignments to those geometries. And then we'll perform the analysis for various load cases. And the results of these cases will be reviewed, and accordingly actions will be taken, either to reiterate analysis by updating properties, or the results are fine to proceed with the design. So design is the last stage. It's a post-processing thing where we have control over the load combinations to be involved for the design, and design preferences and overrides if any needed. First, let us discuss a few modeling related aspects, and then analysis, and then the design, before we enter into the SAFE program with some examples. So primarily, modeling options have two ways of creating the model. One is create the model within the SAFE, because SAFE is a standalone program. You can create models directly, foundation system or the floor slab system. Our focus would be on the foundation system. So we can generate the geometry and joints where the loads are acting. And you can import loads from other programs instead of manually assigning through database editing tables option. The other one is, being a software of CSA family, you can import models from ETABS directly, which can include both geometry and the loads. So this also supports SAP 2000 and the CSA Bridge for the same purpose. In the ETABS, so one heads up that we want to give is that when dealing with the response spectrum cases and for the foundation analysis, we suggest that these dynamic cases are converted into equivalent static. So for converting, you can extract the story forces for these spectrum cases. One example is shown here in the table, where the forces reported are the cumulative values. So you need to extract per story level force. So difference of the consecutive stories will give you the force, and this force set can be easily applied as a user load, which is going to be a static load pattern. And that is also shown in this screenshots, one for X, one for Y. And the soil support, which we are going to apply as area springs, is a one parameter Winkler soil model will be used, and that are defined typically for the vertical direction as shown in the screenshots here. And it can be compression only or tension only or elastoplastic. So for all of these, it requires a nonlinear load case. If the case remains linear, irrespective of these specification for the nonlinear option, it is going to behave linearly. That means tension and compression both exist. We'll come to that more on later. So in case you're modeling some tension piles, that can also be modeled using frame object with zero compression limit or a link element using nonlinear hook property. This program gives you these options. But for both of these, we require nonlinear load cases. Right. A few discussions on the analysis. So I'm only giving the brief thing about the analysis process because we have discussed several analyses in the past. So basically, we are going to get the analysis results for those linear and nonlinear settlements, soil pressures, shell forces, element forces directly that can be read, or you can add strips that will give you an integrated shell force. Right? These are the things that are required in your foundation design. And for soil pressures, typically we'll check for the limits, and we can get those outputs in terms of graphical output. We see in this picture that will also show you the minimum and maximum with contours. So quickly understand the behavior or the response of these soil pressures, whether they are under compression or any tension is existing. This is from a linear static case. All the values are negative, the minima and maxima. That means it's under compression, no tension exists. So we have another non-structural geometry, which is called slab panels within the program. If you draw those, one of the utility is to get the soil pressures in tabular format. So I have shown it here. I will show it in the model as well. One is showing maximum minimum pressures for each case. And the other one is showing the I think the picture is wrong, but the other one is going to give an envelope of all cases. So you can directly see from all the cases what is the minimum and maximum. Both are available. Sorry for that wrong picture, but I can show it in the model later. And if you are performing uplift analysis, so you need to ensure the model is stable for linear static analysis and review the analysis run log to ensure everything is fine. And then the modeling requires lateral restraints using a spring point, corner springs or line springs that is going to resist the lateral displacement. Or you can also run this using the 2D plate analysis, right? But it should be noted when 2D plate analysis enabled, it ignores in-plane forces. If that is significant, you should use full 3D analysis, but providing lateral springs as restraints for the lateral directions. So troubleshooting can be done, again, going back to the run analysis log and review the displacements, and you'll be able to identify something is out of control. And so the reason is repeating here for the response spectrum case, do not use response spectrum analysis because results are absolute. That means no sign or direction when uplift is a nonlinear direction dependent phenomenon. Now, a few things about the design. So before starting the design, we'll be setting the preferences, starting from the code, and then parameters related to the factors, and cover to the slabs or the footings, both are same, and preferred bar size to work out the effective depth in the respective directions. And beams are present, then beam cover a similar fashion. So there are two design bases. One is finite element based, then the other one is strip based. So finite element based is always available when you perform the design, irrespective of the design strips are drawn or not. So you can always refer to this output, but we recommend the design strip method over the finite element based. So you can use the finite element based output when the design strips cannot be drawn due to its geometry, the skewed nature or something like that. Then you can always use the finite element. So this is independent of the design strips, and it provides you option with averaging for refining the display. So everything will be graphical output for this design basis. Strip-based design. So we have to draw a strip of a definite width or varying width from the starting to end point. This is typically drawn from end to end of a raft, or you can also break it between columns or the supports. It has automatic control points. So control points cannot be edited. It is internal. So you can refine it by introducing more design strips. You want more design session locations. It typically picks up the mesh session location, but in some cases, because the uh, angle of the local axis of the slab and the design strips are not matching, it will try to get the cut internally. Okay? So it is a very complex thing. So it is automated completely within the program. And then the strip will integrate the forces and give it to you for the design. And it involves wood armor method for the moment integration. That means the twisting component of the forces will be included in the primary directional moment. So I will demonstrate quickly in the screenshots. So when you see a strip moment, let's say this is decon S2, and it's an isolated footing, and the value is 1083 at the column point. You will see strip force reporting before and after. Right? This is the design location, and then before, and then the after. You have this reporting, but in this case, it is very symmetric, so the values are same. It can change depending on the configuration and the chain distribution of the forces. But when you see in the design output, the moment used will be different. That is because of the Woodhammer method. So that is demonstrated further in a calculation. And see, the analysis moment is simply the summation of the elements. So if we take the shell element forces output, you can see the nodes. So purposefully, this footing is meshed into 4 segments so that it will be easy for demonstrating this. So this line, the vertical line and about the horizontal direction, is the station location where we are calculating the strip force. So there is before and after. So both are done. So you can look at any one. So the pink color highlighted portion is on the before and the blue color highlighted is on the after. So you can see this 9 and 13 and 9 and 12. Right. Look at any one, let us say the before, and you can see the element width is 2 meters at 4 meter by 4 meter footing, and it is 2 by 2 element width for these joints. So it is M11 average, and then the next element between 9 and 13, another average. And then the summation of this will give you the analysis moment, analysis strip force. Then if you look at the design, then it includes the twisting component, which is M12. So this is getting added here, and this is 1206. Same goes for after. I hope this clarifies the analysis strip force versus the design strip force. Right. And then for the design, for the flexure, code-based parameters comes into picture. So it uses whether it is a T section or a rectangular section. The stress and strain assumptions are shown in this picture. And then program determines the factored axial loads and moments for each strip. And then the flexural reinforcement for each strip is reported. And program performs one-way shear check always that can be found in the slab design output under the display type shear reinforcement. This is available only with the strip based, and it should be noted that it is performed at all design stations. So it will not perform only a D away, which can be done for simple cases, but for a complex force distribution like a raft, combined footing, etc., always requires check at multiple stations. So program does it. So the user will have to check this at D away from the column face, whether to include or exclude. I will show this in an example. For now, it performs at all station location. Next is check for punching shear, two-way shear check. So it calculates the punching perimeter, the critical section, right, D by 2 away from the face of the column or the pedestal. And it also considers transfer of unbalanced moment, determine the concrete capacity, and determine the maximum shear stress. Shear stress is computed assuming a linear variation along the perimeter of the critical section like this, and the peak one will be used. And that divided by the capacity will give you the demand capacity ratio. So program reports it as a TCR, not the stress value, when you bring that punching check output. So when you right click on that output, then it will give you the details of the calculation. So the mulching shear check involves an internal algorithm that calculates the ineffective area and exclude it. For example, like openings, you can see so only these beyond those opening region, tributary region, then it will use this, and it also detects the location, the column location, whether it is an interior column or it is at the corner, and accordingly only two edges or all four or three will be used. A detailed overwrite is also available for the punching shear in case you find the auto detection is not sufficient. For example, you can specify the location type manually. You can see currently it is shown as auto, but you can set based on these location type. And then you can also specify the perimeter manually by drawing a polygon for special cases. And you can also override the effective depth to be used. So when you set all of this, it's going to update the design based on this input. Right. The last thing would be the design output. You are going to get everything in a graphical use interface. And then you can also get those in a tabular format and terms of report. So you'll get a summary and as well as an envelope output. Okay, let us switch to the program, and I will show you a few things related to the modeling directly in the program. So this is the ETABS model they used for this demonstration for exporting the loads from above to the SAFE program. So typically for export, we'll use the export option and story as SAFE, and we'll have to select the second option, explore for loads and loads from above. Since analysis is not performed, we can quickly do this. Right. Okay. So it is using equivalent static method as well as spectrum. So we export. Export the base level and all the loads from above. So in this model, I have used only the fixed type restraints to the base. So only the loads will get exported in this case. You can also model the footing or the raft here and export it to the SAFE. So geometry will also be taken to the SAFE. So load cases, you can select all, and then you can do the export. Right. So inside the SAFE, to start the SAFE program, and then directly you can go to the import and do the SAFE F2K text file import. Now this. Right. Now you can see the joints, and there is a shear wall core which has been transferred as an equivalent beam, but with the support reactions or the loads from above. So what program does is it creates load patterns of two sets. So one is all the load patterns, the same name, dead, live, EQX, and EQY, which we saw in the ETABS. And then another set for the same with the suffix above. So two sets are maintained. So the underscore above suffix load patterns will contain the loads. Now you can right click and you can see all the above will have. For the response spectrum, the data is transferred as model data, not as a static force. So you can see the mode reactions here. So we had 12 modes, and 12 modes data is available here. But the response spectrum case, related data is available as a table, which is internal to the program. You cannot see this. Maybe you can see it in a tabular format, but here, under the load case, you will find the model and the response spectrum case. So if you try to see this, there will be no information, but this spectrum case was imported from ETABS. For details, see ETABS and safe model. However, the information is available under the table, show tables, load case, imported load case, spectrum. Let's see, acceleration data, so the scale factor. Model as well as its function. Function and the model. So the model data will contain the model mass, model stiffness, so participation factors, all data relevant from the spectrum case will be available here. So when you're performing the analysis, it automatically converts this into cases, and you will have the forces acting on the joints. So the only for the uplift case, we are recommending not to use the spectrum, but typically that will be a check always in our foundation. So you'll be anyway requiring this static forces. So that's the recommendation that we convert these response spectrum, and it'll be easier for you to check the pressures based on those uplifts, especially for the seismic cases, easily. All right. Next is in the modeling. Modeling, I'm going to skip this, but briefly, you can create the material properties, section properties, and draw the raft, right, etc. And what you can also do is using the edit option, you can quickly add the design strips. Add design strips using grids, and it will create the design strips as well. I have created the model already, to save some time. I'm going to pick that up. I'm going to use a model in which I have converted this into equivalent response spectrum static force, which I demonstrated earlier. So all of this are now static. So no model information is available. So all are static. I'm leaving it to explore the generation of the strips that are using the edits, or you can use the draw and draw the strips manually. This is equally spaced, so I can utilize the draw edit design strips, and it has created it for me. So important thing about the strip is it requires Right click on this, you can see this starting point and this end point. And the geometry, it carries width information, what is on the left, what is on the right. So 1 meter and 1 meter, totally it makes 2 meter wide strip for the start and the end. So I'm maintaining uniform width. And for the design, and click on this again, and you'll get the overrides form directly from here, where you can update the rebar material. The concrete material is coming from the slab itself, but the rebar material you can change if you are providing different rebar for certain regions. So the option is separated from there. We are using Fe500 rebar here within this material. And then we are grouping this as layer A and layer B. All the horizontal ones are layer A. All the vertical ones in the Y direction are layer B for convenience. So it doesn't have any design implication, but that's only the grouping. Only one thing except the effective depth. So which layer is inner, that one we specify in the design preferences, whether B or A, accordingly the effective depth will change. May not be significant, but it uses appropriate direction-based effective depth calculation. And you can have column strips and middle strips. Column strips, as the name suggests, you can run these strips. And the columns are middle strips in between those as a filler if the spacing is too much. Here I have used both. So one is column and one other one is intermediate middle strips. You can see here. Let me update the graphics for that to clearly show. Before that, we also have the cover preferences, which directly comes from the global setting, design preferences, or you can also specify directly to this strip if it is changing. Right, so you have this overrides form for this purpose. If I check only layer A, now I can see only the horizontal ones. So this yellow stripes are this middle strip. So in design, there is no difference, but for convenience, you can group them. But this is typically utilized in the PT slab where you use column strips and middle strips for distributed and grouped tendons. All right. Now quickly, can go ahead and perform the analysis and design of this. It should also be noted that these column locations, the joints, will also contain the load size, same as the column dimension. This is automatically coming into the save when you're importing this. So when you right click, you can see the loads and then the X dimension and Y dimension, right? So this information is utilized in the punching shear check with this dimension, and then D by 2 will be added. If this information is 0, then D by 2 is directly from that column joint. It could be incorrect. So it should be updated accordingly if needed. All right. I've taken up the raft since I wanted to cover the import option. We'll switch to an isolated footing as well as a combined footing shortly. So after the analysis, you get to see the deformed shape, go for any combination and create multiple combinations for checking the pressures. For SLS case, I'm going to quickly create dead and live. And I'll Also add the force reversal for the X, and similarly you can do for Y direction, also the equivalent static of the response spectrum. So you can create those many combinations here. Now you can go ahead and see the pressures. Check the deform shape, and then we'll switch to this cellulose, and you can see the deform shape, basically the settlement. So for this model, I have used a single soil spring support as a property. It can also be varying because the soil properties may vary uh, in a larger raft. So you can model different portions with different soil springs. So this one is a single one, and you can see settlements here. So see the settlements for the positive X, right? Pressures are going to reveal this uplift. Yeah, this is gravity only. This is with seismic. You can see the pressures are -54 and -137. That is, both are under compression. There is no uplift. Okay, so, but you should also work on the iterations of increasing the raft size based on the pressure limits, allowable limits. That is part of the iterations. Right. Next, quickly, and go to the shell stresses and forces, where you can see moments M11. By default, the local axis of the shells will be oriented with the global axis X and Y. So this is 1 horizontally, and vertically it is 2. So M11 is horizontal direction. You can see the forces. For quick estimations, you can draw section cuts and get the forces. This is a larger raft, so may not be that useful, but you can locally apply a cut, and then you can see, you can save the cut and use it later also. But for now, we are skipping those details. Right. So V13 is the shears, out of plane shears. Right. You can see the variations. Right. So in this model, I kept it very simple, covering the basics. But here to the columns, you can add the stiff area element to model the junction, to improve the behavior as well as the force distribution. Okay. Now I'll jump to another example where I will discuss few more things in detail there. So we have isolated footing. Simple isolated footing. And here this green area object represents a panel which I had drawn. And check this. So this is the model. Right. So for the analysis, you can have the meshing, leave it to the auto, and then you can specify this uh, to a finer size when you are doing a smaller isolated footing. So I have kept to 0.25 meters. And in this one, stiff area has been added. The default stiff area, which is nothing but 100 times of this slab property to mimic that stiffer junction. Now the distribution will change and the force output now you can see the force at the face will be significantly higher compared to this stiff area junction. So this way you can achieve the economy in the design. So now the design is performed and several station locations, like when you go to the display, show tables, design output. So we have slab summary as well as detail. Select both. Summary is going to give you, let's take only one strip. So this one under start, middle, end, start, middle, end. So the two cantilevers. When it is a larger one, then you'll see multiple segments of this. It is an envelope of everything. So this one is going to simplify the output, which is actually done like this. So you can see in the detail for CSA1, let's filter this. And there are 19 locations of output available to you, right, along the length. Approximately every 250 mm, you can see the station location and the design of. So flexure and one base shear. So status is okay. Graphically, we can bring this. Okay. Please note down this rebar requirement. I'm going to change the preference for the flexure, and you can see shear reinforcement is 0 currently. This is because of the design preferences I have set for the design. That is increase flexural rebar for enhanced concrete shear capacity. So by default, it is no. I made it yes, so that I avoid modeling any links or detailing any links for the execution. Now, if I set it to no and perform the design again, you can see a reduced rebar, right, at around 1400 to 1500. Now, if you check the on-way shear reinforcement, so it will show you some requirement. Since it is designing for all session locations along the length of the strip, so it is showing only at few session locations, especially at the column location, near to this column location. But the engineer should be able to handle this, because during detailing manually you can also increase the flexural rebar to avoid this, and you will be reading this away from the face, D away, and see whether at this point shear rebar is required or not. If it is not, you can ignore this. That's the use case of this output. Wanted to show this. Okay. The next one is on the pressures. Pressures we have already seen, right? Right. Graphically. So I have drawn this slab panel just using this draw slab panels. We can draw it as a single panel for per footing, or if it is a big raft, you can also break this into, for example, you can also draw this into four quadrants. So each panel will give you the maximum and minimum if that is required. So after modeling this, you will be able to see the analysis result summaries, uh, soil pressures. Without soil panels model, these will not be enabled. So please take a note of it. So one is summary and there is enveloping of the summaries. So the summary, which is going to show you for each case and combination, and the enveloping will be enveloping of all for this one single panel, right? So you can, there might be multiple combination. You will not be able to check manually, so you can get the envelope quickly from here. This is one important output which you require always. Okay, let's move to another one, which is an uplift. It's a simple example because I want to give you the fundamentals here. So this one is subjected to a moment and there is an uplift on one edge. Okay. So what I did, under the load combinations, we have the standard load combination definitions should be used in the design. And I have created SLS and I selected all this and converted into a nonlinear case. So when you, for the first time, perform the analysis with a linear basis, you'll be able to see the uplifts, tension, or the pressures, positive pressures in the soil pressure output. Then you'll have to perform this, right? Right. I kept one linear combination just for comparison. So the another one for uh, nonlinear case. Now program converts this into nonlinear case. You can see dead load 1.5 times. This is dead and live 1.5 times. And then the unfactored dead and live. But all of these are nonlinear static. One important thing about this, when you're performing nonlinear, make sure the area springs are defined as compression only. That should be the default one, but it should be compression only. And then the load case should also be nonlinear case, have this effect. The other thing is, whenever you're performing a nonlinear case, each footing should be in a separate file. Do not combine them with, like there is one more isolated footing here, multiple isolated footings in one file. That is not recommended. You should avoid doing that. Better to keep it in individual files. Right. Now let us quickly check the pressures. That will clear everything. I'm taking only the SLS and the other one as SLS linear combination. Now you can see in this footing, the left edge is subject to uplift. You can see positive value 28, about 30 kilonewton per meter square positive value. Right? That is the from the linear case. Right now we have performed the nonlinear case, and then you can see the program could manage this by for uplifting. There is no pressure, and that the pressure here will be increasing accordingly. Right, and then these nonlinear cases are already converted for the design combination. You can directly perform the design of this. So there isn't much for the user engineer to do, but if you want, you can modify this further. But program is capable of handling this uplift. Okay. Let's move to the next example on uh, pile cap modeling. Okay. The simple combined footing. The pile, the typical modeling would be modeling them as joint springs. So for that, and how to create these joints manually. So that's why this draw joints, special joints are available. You can create joints by providing some offset and take the reference of this column point and create joints and then replicate them wherever needed. Or draw it manually. Or you can also draw it somewhere closer to a location and align it with coordinates. So all of these options are available for your modeling. So this one is a simple strip arrangement of the piles. So the pile is defined using a spring pile. There could be multiple piles, so you have to define a list of piles, and it is carrying. Sorry, this is having a capacity of 7,000 kilonewton per meter. The stiffness constant. And these joints are assigned with this point springs. Now this footing does not contain any area springs. I've removed it. In some cases, depending on the configuration of the piles under the pile cap, can create, for example, two pile can create some uh, huge rotations about because it has only the axial stiffness, no rotation stiffness for the piles or the point springs. Then it might create some trouble. So in such cases, you can apply a small uh, area springs to the pile cap that will contain the rotations. So you can see large deformations in some cases. So you can overcome with those. That will not affect the design significantly, but those are the alternative ways that are available to control the large deformations. Okay, so in this case, this is well supported in both directions, so no, you don't require such. So one additional thing that I made is to these joints. So I want the program to check the punching for this in the design. So what I did, I added a very small load with a load size. So load size is important for these joints for the punching check. And I also updated these joints under the slab design for the punching check with the location type as interior. Otherwise, the auto uh, will kick in and it might take a different punching perimeter. Being this closer to the joint, it will take only one. If you want that, you can allow it to the auto detection of the pile, punching perimeter for these piles, or you can override this as needed, right? With this update to the model, you can perform the pile cap analysis and design. What we will see is the reactions on the piles. So I have applied a lateral force. And now we can see this is for the combination. Just for the case, you can see some tension developing in this, but that is only with the lateral force. But when you're combining with the gravity cases, then this is the actual reaction, and all are in compression. The reactions are vertical, upwards. That is no tension in the piles. All right. Next, you can perform the design. Design is already performed. Now we can check the design output based on the strips and use like this, and it will going to give you the visual output, right? You can also modify the strips In those locations, maybe if it is a larger pile cap, then you can also draw strips over the piles where you expect the reinforcements at the top that will also be uh, given in detail depending on the strips how they are drawn. So drawing the strips is arbitrary. Typically, the strip width is used 1.5 times, 1 to 2 times of thickness on the left and on the right in each left and right. So that way, you can have some people will tend to have a conservative estimate of these forces and the design. So they can have the 1 meter strips across. That is going to give you a conservative design of reinforcements as well. So, but those things, since being arbitrary, I'm going to leave it to you. So now I'm enabling the punching shear capacity ratios. Right, the column location updated as interior through overrides, and it is checking the demand capacity ratios 0.16. Okay, so that is a validation program. Sorry, example in the design manuals under the help documentations. You can find them how the program computes it. All right. And I think with that, I covered most of the aspects. But if you have any specific things, then please let us know. Let me try to answer a few questions under the Q&A. Yeah. Can we design strap beam footing in SAFE? Yes, you can do that. Our recommendation is you can draw if you, the current combined footing which you're seeing instead of uh, the beam modeled as frame, you can model them as a shell element. So just draw an overlapping, let's say 1 meter wide strap beam and depth is 1 meter. You can define a shell of 1 meter thick and draw this connecting the columns or extending beyond that, and you can do that. Okay, regarding the meshing, which one to use, generalized or rectangular, you can use either. Uh, it doesn't matter, but the general is given to handle more complex geometries, like let's say you're having a circular and a skewed shape, where rectangular meshing is not going to help you. Then you can go with the generalized, or generally you can use rectangular for most cases. For these examples, I've used rectangular only. If the forces or the stresses are sensitive in certain locations, mesh size will affect the design and other responses. Yes, that is expected, but you can uh, uh, make the average instead of getting into the element level details. Can use the design strips that should give you a reasonable output always. Because handling the finite element output will be a cumbersome process. Uh, Maybe one or two we can handle, but for a large design office requirement, you should use the design strips. Yeah, averaging you should use when you are reviewing the graphical output so that it is also comparable with your strip design outputs. Yes, there is one pertinent question, that is punching shear check for shear walls. Uh, Punching check is for a single joint, which is a column location. For wall locations, uh, it is not performed. The reason is that there are several joints lying along the length of the wall, even it's a single planar wall or a multi-legged wall core, then the punching perimeters will overlap, right? So such a condition and the design procedure both are not available uh, for the design to implement in the program. So our recommendation is, if you want to do this, then you'll have to do some alternate ways of getting this. Maybe the static forces can be converted in, the joint forces of multiple joints can be converted into a single joint and perform this check. Maybe in ETABS itself, for the punching check, you can convert the bottommost story as a frame just for this check, not for other design outputs. Only for punching, convert into a column frame and export it to SAFE and do the checking there. But beyond that, there are no other ways. So the crack width that is implemented uh, based on Eurocode, I think the parameters, the K1, K2, K3 parameters are the only things that are available to you to modify, and you can get this crack width check. It is very similar to Indian code, so you can use the same feature. So only one code base is available for this. Yes, I'm sorry. Yeah, this slab definition, you can use the shell thick, which includes the shear deformations. Right? So, as per the code also, we require to include shear deformations always. It will not be significant, but still, being a thicker slab, the footing or the raft, can use shell thick for the slab property definition. The strip area, the default definitions, in property modifiers used within the program are sufficient. No need to modify unless there is a need, then do it. Yes, pre-stressing can be introduced in these footings as well, but you need a safe post-tensioning level of the program. Standard will not have the post-tensioning options. Okay, I hope I have answered most of the questions, but there might be few unanswered. Sorry about that because we are running out of time already. You can always write to us for any specific queries related to your model and share the model support@csiespl.in. We'll be happy to uh, clarify those questions. Right. Thank you all for joining today. I hope it was helpful. See you in another session.